Okay. Okay, let's get started, guys. So last week, finally, we finished the crypto background part. So this week, we will discuss about authentication. Next week, we talk about access control. So before we get started, two announcements. First, homework 1 has been posted on UBNerds. You have almost 10 days to finish the homework. So this is the first homework of this semester. So I hope everyone strictly follows the AI policy. We have the TA, we have the grader to cross-check all your homework to make sure everyone finish your homework independently. Also, next Monday, I will be out of town to attend a conference. So instead, I will deliver next Monday's class online this Friday night. You are not required to attend. I will give you the link later. You are not required to attend, but if you want to ask questions, you can attend. Then after that, I will post the video. So several times this semester, I will be out of town, and we're going to do this kind of online sessions. So today we will talk about authentication, and we will spend 3 sessions on authentication. I have been working on all kinds of authentication myself. So some of you took my software and system security class, know me as a system and software security guy, but actually I also do authentication a lot. So I will use my own experience and also from the books to teach you what authentication is about, where the future of authentication is, in my opinion. So the word authentication, we have seen this. We have seen this in MAC, message authentication code, right? So we use hash functions, we use symmetric key encryption to do MAC. So MAC can help us confirm a message come from a stated sender, which means the authenticity of the message. MAC can also guarantee the integrity of that message. So we know that message has not been changed by someone in the middle. Okay, so that is what MAC for. That's what I call message authentication. However, this week we're talking about a different authentication. We're talking about user and entity authentication, which means we need a user or a computer or device to prove his, hers, or its identity to another entity. So you do authentication every day. You turn on your laptop, you need to type your password. That is authentication. Your phone may have a fingerprint authentication and others. That is also authentication. You are proving to your laptop and proving to your phone you are the owner of that. Okay. So as you can see that the word authentication has some broad meanings, and basically refer to the mechanisms to ensure entities are who they claim to be, and they can also use for in MAC to prove data has not been manipulated by unauthorized parties. And the user or entity authentication is just one type of authentication to verify users' identity. If such verification is successful, then usually the user is granted privileges and permissions. Only after you type your password and your password is correct, you can use your laptop, you can use your phone. Okay. So authentication has been in computer systems for a long time, since our computing systems started to support multiple users. So in general, during an authentication protocol, there is a verifier. You log in your computer, the verifier is a computer. The computer gathers evidence that you are the owner of the computer. And a good authentication protocol should have these properties. So first, the honest parties should be able to successfully finish the protocol with their identity accepted as authentic. So we should allow the legit users to use the computer, right? And it should also be difficult for attackers to impersonate a legitimate user. Even if the attacker have observed a large number of successful authentications by a legit user, still the attacker it should be difficult for the attacker to successfully authenticate. So a lot of authentications, they actually require a step called the user registration. For you to log in your computer, you already first set up your account and set up a password. That is a user registration step. A lot of authentication require that. So right now, there are three types of authentication. Sometimes we call it identification mechanisms. The first one is based on a shared secret. So the user knows a secret, like a password, a PIN, a secret key, and other information. So this is a secret you share with the other party. So the other party believes that only you know the secret and use this one to authenticate you. This is the most popular authentication, not necessarily the most secure way, but like all other security solutions, the one we are using are not really using, the practical ones are not necessarily the most secure ones. The second type of authentication is a user possesses a token. So the token may have some information. The token may have some computing capability and also have some secret. So we will talk about this type next week. And usually this type will be combined with some crypto protocols. The first type, not necessarily. Sometimes yes, but sometimes no. Then the third type, we call it biometrics. So users has a physical attribute or some physical attributes inherent to the user. And the authenticator will use those biometrics to authenticate the user. We will talk about this this Friday. So some examples here. The first one is based on something users know, like a secret. For example, all the website you're logging right now, we use an email address as your account, and we use a password, usually just a text-based password. Then also here in the middle, you can see something, a picture. You draw a gesture on the picture. This is something called picture gesture authentication, introduced in Microsoft Windows 8 almost 10 years ago. We will talk about this one later, actually. Then your Android phone have this, those 9 dots. So you just choose a correct path on the dots as your password. And your iPhone used to have like a PIN password for 4 digits, 6 digits. So those authentications, the device, the verifier, knows a secret. You share the secret, you build a secret with the device. Some of the secret has to be very accurate, like the password. Those are just characters, have to be accurate. The Google passes, the Google Android, what's that called? Pin lock, whatever. So you also need to be accurate. But for example, the picture password, you draw something on the picture, it doesn't have to be so accurate, the location. So the password system can tolerate some little errors there. The second type is the user possesses some token. Some tokens, they are just a simple certificate, like your birth certificate, like your driver's license, like your UB account, UB card, right? So those certificates are issued by a trusted third party. Driver's license are issued by DMV, birth certificate are issued by, I don't know by whom, but they are trusted by government anyway, by some trusted party. Then some of those tokens, they have computing abilities. So for example, RSA has this RSA token. I don't know if anyone is still using this, but 10 years ago, it was very popular. It generates some 6 digits random number every 1 minute. And when you log in, you need your account, you need your password, and you also need that 6 digit randomly generated on that device. And also, like if you drive, you may have an Easy Pass to pay your tolls. And the Easy Pass, that is also a device that do a challenge response protocol with the roadside devices. Also, your credit card. Some of the credit card right now, most of credit card right now, they have a smart card there. That small thing is called a smart card. The smart card has its own CPU, its own memory, and also secure storage to store secrets. So when you make a payment, the bank, the behind will actually make some challenge response protocols to verify if this card is a real card. So those are token based, but you can say those approaches are based on crypto approaches, and sometimes they are used together with a password. Also, there are a lot of biometric authentication based approaches. Some of them are already deployed in our real devices, like fingerprint, like face recognition. Those have been widely deployed in our phones, Android phones, iPhones, for almost 10 years. And also, hand authentication is a new thing. So the picture here is a hand authentication, because no matter it's face authentication or fingerprint authentication, people worry about the privacy. People do not want to give their fingerprint to Apple or Google. So, but usually people are less concerned with the hand privacy. But a hand has a lot of information that can be used for authentication. Also, the other two pictures I'm showing here, one is called the heartbeat authentication. Just using your heartbeat, everyone has a unique heartbeat. If we can remove the noise, find out the reliable signals in everyone's heartbeat, we can use that for authentication. Also, the last picture shows a brainwave authentication. So you can see a lot of papers on those topics. They are not necessarily in the market yet, but in the future, they do have. I believe it's possible that we will see them in our daily usage in 10 years. For example, fingerprint and face-based authentication, we only talk about them in academia 10, 15 years ago, but now it's on everyone's phone. So a little bit game here. So we have seen a lot of biometric authentications in Hollywood movies, actually. So one of my habits is to collect those. So let's say if you can, well, the first one, obviously, that's Iron Man. So what is Iron Man's authentication method there? Everyone? Yeah, exactly. Voice, right? Iron Man is a voice-based authentication. Then that one there is, I believe that's Mission Impossible. So in that picture, you can say the user is walking, and the way he walks is monitored on the device and using some algorithm so this is called gait authentication, based on the way you moves. How about this one? This one, left button. Anyone recognize this one? Which movie? Which one? No, not Matrix. Which one? This one. Yes, that's Tom Cruise. That's an easy one. Yes, that's Minority Report. How about this one? So we do see a lot of eye authentication or iris authentication or retina authentication in many movies. Minority Report has that. Also this one. This one is actually Blade Runner. This is the original, the version of Blade Runner. Use eye authentication to find what is it called? Replica. Okay, now how about that one? The one in the middle, right hand side. The idea there is to take one drop of your blood and do a DNA-based authentication. So which movie is it? Okay, so you guys work too hard. Do not say enough movies. Okay, so that one is from, how do I pronounce that? Gattaca from Ian Hawke. It's an old movie. So that's just take one drop of blood and do a DNA sequencing to authenticate users. So those are biometric authentications. We will talk about biometric authentications in this Friday. Okay, so you can see that, first of all, we usually combine multiple different authentication methods together, and that's why we call it second factor authentication or multi-factor authentication. For example, a PIN-based authentication is often used with a physical device. Like when you swipe your debit card, you need to input your PIN. When you swipe your credit card, you don't, because there's a law behind that. When you swipe a credit card, you cannot use your PIN. The biometric authentication sometimes is used combined with a password and or physical token. So those authentication methods, they are not necessarily secure. Friday we will compare all those methods to say why we are still using some of them, like text-based password. We are still using it even after 60 or 70 years. And no one really thinks that's very secure, but we are still using it. But why we are still using it? So we start with the password authentication, like text-based password. So a text-based password is just a string of characters. And usually the user will choose the password. Okay? So when you register on your computer, on your account, you choose a password. Before the password manager, now the browser has a password manager to help you randomly generate passwords. That's very secure. But before that, like 5 or 7 years ago, what are you using? You are probably using the same password, or you change the password a little bit for different website because you cannot remember so many passwords. And so how this password authentication works is the user will send the username and the password pair to the server, to the verifier, and the verifier will just compare the password and to say if they are correct. So we talked about this last week. So how do we store those passwords? The most straightforward way to store passwords is just the plain text. Just to store the password. Do not hash it. Do not encrypt that. I don't know how many websites are still doing that now, but it used to be a lot of websites doing that thing. Okay. The problem of that is those websites, the verifiers, they are not necessarily secure, right? They can be compromised. When they are compromised, all those users' passwords are compromised, and the users have the tendency to reuse password in different website. So your password in website A is compromised, and attackers may use the same password, your email address, try to log in your account in website B. Okay. So to mitigate the problem, what we used to do is just use a hash function. We just used to MD5, SHA-1, but I already showed you last week. Now a better approach is to use some password hashing function, not a regular hash function. The weakness of this kind of password is obviously they are subject to replay attacks, which means if your password is compromised, then the attacker can use it. you can replace that, right? So for attacker, what they can do, if they, let's say, they get the hash value of the password, they compromise the website, they do not get the plain text password, they only get the hash value. What they do is they do a exhaustive search and try to check all the password in the address space and say which one matches the hash value they get. Also, they can just remotely try to log in your account using different password, right? But all those approaches, you can see, the assumption here, implied assumption here is the attackers believes all the passwords, they have the same possibilities. All the password in the password space have the same possibility to be a password. Okay, there's a uniform distribution there. But obviously, this assumption is not correct. Users, they tend to, because this is user choosing secret, users tend to choose weak secret. That's why we have something called a dictionary attack, where attackers collect a large corpus of passwords from compromised websites from other places. Those are passwords people usually use, and we just guess from those passwords. It's higher probability that everyone is reusing the same password. So also back to the hashing part, we talked about this last week. Let's say like 5 years ago, you have a password, then the website will just hash your password and store it. So when that website is compromised, that hash is compromised. And if we compare different people's hash value, if they're the same, we know they are using the same password, right? Because hash function is a deterministic function. To solve this problem, then we add another random number with the password. So we do not only hash the password, we hash a random number which we call the salt. We call the salt, concatenate the password, then we hash that, store that. This is what we used to do, use a simple hash function. Now we do the same thing with a password hashing function. So even if a website is compromised, a lot of hash values are compromised, you cannot clearly make the collections between different people's hash values, even if their password are the same, right? You have to try all the sorts there. So we also have other measures to improve the security of password. First, which all the systems use right now is limit the number of unsuccessful password guesses. I think iPhone has this limitation. If you guess too many times with the wrong password, the iPhone will be locked forever. So you cannot use that anymore. Also, websites, they always employ some kind of password rules. Like you have to use how many strange characters. Your password has to be 8 or 10 characters long, right? So those rules make people to choose longer password fall into a bigger password space. That's the purpose of those. And also to slow down the password verification, we can hash that many times. So that's the idea of password hashing actually. Also, we protect the password files, no matter they are hash values or plain text, we want to protect them. So the old Linux system, the password was not protected. 20 years ago, I believe 20 years ago, the Linux system, the password is just stored in etc/shadow. Password, the hash value, the MD5, the password was just stored there. So everyone can access. Now this file cannot be accessed by anyone except the root user. Also, we ask people to update their password, which is called password agent. Some organizations will ask people to update their password every 3 months. But this is not always an ideal case, because when you are asked to update a password, what do? You change your old password a little bit, right? Because you want this process to be fast and easy for you to remember. You just change it a little bit. Okay. So that's why actually there is a paper on this. I will show you later. The assumption is they compromised a website which has users' password hashes, but those password hashes were old password hashes. They're not the latest versions of users' password. Then their assumption is the users will only change their old password a little bit to get the new password. That's why using that heuristic, they can still guess the password quicker. So the password strength has been a research field maybe from the 90s. And personally, I observed a lot of research papers in this topic after 2010. Many papers talking about the science behind password guessing. How can we guess password faster? How can we find the patterns behind passwords? We will talk about those in Friday, actually. And there are many tools developed for password cracking or hash value cracking. And that's why in the last 5 years, something really useful, password manager, has been very popular. In browser, the password manager will always generate a random, very secure, very long, and random password for every website, different website you are using, and store them in your browser. You don't need to remember that password. And you only need to remember your root password to access the password manager. So far, that's still a very secure approach. If you are still not using password manager, you are still using your own 5-6 character password, you should consider changing that. For example, I keep saying the password, if they're not using password manager, then you choose a password. So user chosen password, users always choose weak password. Let's say you choose a password 9 characters long. Okay, so that's actually quite long. It's not easy to remember 9 characters. If you have accounts in 100 websites, it's not possible for you to remember a 9 character password for each website. Not possible. But 9 characters is actually the password space is quite big. It's like 10 to the power of 18. It's very big. If we just brute force, it may take us thousands of years, even more than that, thousands of years to guess. However, users, they choose easy to remember passwords, weak passwords. So this is a paper I just talked about. This is a paper published maybe 12 years ago at CCS. They acquired a large data set of user password hashes. It's old password hashes. Then they use that to guess the current user's password. Even though they are hashes, they are able to guess the password faster. So besides those text-based passwords, there are other passwords like picture-based passwords. There are also image-based passwords. Those have been proposed in the last 15 years, and some of them even went to our production systems. And that's what I'm going to discuss next. So how many of you used the Windows 8 before? How many of you used the picture gesture authentication before? Oh, some of you used it. Good. So this is something came out 2012, I believe. So I was a PhD student at that time, and I remember it was New Year. I say a blog from Microsoft research, I believe. So they say that they're going to introduce a new picture gesture authentication system to replace text-based passwords in Windows 8. And their claim is they did a lot of analysis saying the password space of this picture gesture authentication PGA is huge, is much bigger than text-based password. So it's supposed to be much more secure. I saw that blog. I thought about it. I think, oh, this is a very interesting idea, but I do not agree with their assessment because same as text-based passwords, even if you have the picture-based passwords, users will still choose some kind of weak password. We just need to find out the pattern. So I started a project to try to hack this password system and to understand the weakness. So this is a work I did when I was a PhD student. So let me explain how the PGA works. So in PGA, you choose a background picture first. The background picture basically helps you memorize your password. Then on that background picture, you can do 3 types of gestures. You can tab or place, or you can circle something, or you can collect 2 things together, line something. That's 3 allowed gestures in this password system. And the location of those 3 gestures are basically used as a password. Of course, this one cannot be very accurate. It's not the exact location. That's why there's a little bit tolerance in this system. For example, in this picture, this picture was taken from Microsoft's blog. The password here, you can say, I don't really remember which one is first. Maybe the circle one is the first. You can say there is a circle, so that's the first gesture, and it's the second gesture is that line there, collect 2 nodes. The first one is circle ahead. The third one is just tap another nodes. So those are 3 gestures. So the direction of the gestures, the location of the gestures are stored as a password. So I wanted to understand how secure this system is. In particular, I want to understand what kind of background pictures people usually choose, what kind of gesture locations, gesture type, and also gesture orders they choose. And if we can find some patterns out of those user choices, how can we use those patterns to crack this password system, to guess this password system? So that's what I was interested. So the first step, I developed a website like this. So the website looked exactly like the Microsoft Windows 8 login system, but it's a website. It's web-based. Then from there, you can select a picture, then you can choose your password. Then I deployed this website in a class. I was being TA for that semester. It's back in Arizona State. So in that whole semester, those students, they have to use our website to get lecture notes, the homework, everything. They do not use something like UBNearns, which is Blackboard. So that semester, we didn't use Blackboard. So the students have to use our system. So, we started their password. Then that semester, we had 56 students, and they only choose the 58 unique pictures because, they are not really into my study. They just want to get into the website and find the homework, syllabus, whatever, right? We collected 86 passwords and more than 2,500 logins and try to understand their behaviors. That's my dataset 1. I also collected another dataset. In this dataset, we didn't allow the users to choose the background picture. We pre-selected those 15 background pictures. You can see they have different complexity there. Some of them are very simple. Some of them are very complicated. We want to understand how different users, they will choose their password using the same background picture. And we put this on Amazon Mechanical Turk. We get almost 800 participants there and collected 10,000 passwords. We also ask some general questions about the subject, their general feelings towards this authentication system, how they select a password, how they select a background picture. So the first thing I was interested was what kind of pictures they want to select. Obviously, this is only for the dataset 1, because for dataset 2, they didn't choose any pictures. So I divided these pictures into these categories, like people, civilization, means like buildings, cars, trains, everything man-made, landscape, and the computer-generated pictures and animals. And you can see in both dataset 2, we asked them the question. We didn't really ask them to choose a picture. In dataset 1, they actually choose a picture, but you can see almost 45% people, they always choose a picture of people as a background. Also interesting is category 4 there. In our dataset 1, which was college students, almost 25% of them choose computer-generated figures. So here, computer-generated pictures means a lot of video games. That explains, because a lot of those students were college students, they like video games. That's why the percentage of computer-generated pictures are much higher in dataset 1 than dataset 2. We ask them why or why not you choose a picture of people. Some people say, I choose that because it's easier for me to remember the password. It's more friendly. And some people think it will make my password more secure, which is not really correct, but some people believe that. Also, other people who do not want to use a picture of people, they say that because they are afraid that that background picture may leak some privacy information or also their identity. So they are against that. Then we ask them, which of the following best describes what you are considering when you choose a location to perform gestures? We're not asking what kind of gestures you want to perform, just what are you thinking? Perform any gestures. So you can see in dataset 1, almost 73% saying, I'm trying to find locations where some special objects are. Like a face, like a nose, like a car, some special objects. Another 24% says looking for some special shapes, like a circle, something like that. Dataset 2 is also similar. And also some say that they are looking for some special colors. So you can see there are patterns. That's things we are looking for, okay? Only 3% and 10%, 3% in dataset 1 and 10% in dataset 2. Oh, I have a typo there. It's dataset, I can date set. So that's a typo from 10 years ago. Interesting. Anyway, so only a very small number of people claim that they will randomly choose a location to draw without thinking about the background picture. Okay. So technically, that will give you a stronger password, but may not help you remember your password, right? So the conclusion there is most users, they will draw passwords on some points of interest in the background picture. Then we further studied the type of picture of people. So in dataset 1, we have 58 students, and 22 of them uploaded 27 picture of people, and we collected 31 passwords from that. Each password has 3 gestures. That's 93 gestures. So we find that 38% of those gestures were on eyes. 20% of the gestures on the nose, as long as that background picture is a picture of people. Then 6% on hand or figures. And 64% of the password have at least one gesture on eye. Almost 50% of the passwords have at least one gesture on the nose. And subject-wise, 87% of the subjects, the students, they choose a gesture on eye at least once. Okay, so there is a very strong pattern here. Another very interesting finding is in dataset 1, there were 2 students. They uploaded 2 different versions of Starry Night. Okay, they may just Google Starry Night, get 2 pictures, and they upload that as their background picture. But the password they are choosing, you can say, they are not at the same location, but it shows exactly the same pattern. Okay, so both of them are trying to just tap a star, right? 3 times, tap a star, and that's their password. So to me, that was a very interesting finding because this is something we didn't know we were going to get when we started the survey or study. So obviously, users, they have the tendency to choose a point of interest with the same attribute to draw on. So picture password have the same vulnerability as text-based password. Users will choose weak passwords, basically. And more interesting, I collected the advertisement from Microsoft. So Microsoft at that time, they were advertising this new thing everywhere. The TVs, online, you can see their ads. So I collected the ads, and I collected the ads in different countries. And all of them choose weak passwords. That's Microsoft advertisement. For example, in Asia, the background picture is a kid, and the password was just a circle an eye, circle another eye, and a circle an ear. Okay. South American is lying on arm, circle a head, and another one is lying on arm. Europe is lying an arm, circle a head, and circle another head. So those are the passwords in Microsoft's advertisements. So they are not necessarily secure. So after we learn those patterns, we are interested in how to use those patterns to attack those password systems. The basic idea is, given me a background picture, no matter what picture it is, my attack system will generate a dictionary, a password dictionary for this picture. And the passwords in that dictionary are ranked based on the likelihood of how likely they will be the password for the user. So obviously, this system has to work on some previously unseen pictures. We have a training data set which has many pictures and corresponding passwords. But when we apply our attack system, we need to apply it to a picture that is not in our data set. Okay. So our approach is simple. We automatically learns those user choice patterns in the training picture and the corresponding password. Then we apply those patterns to the target picture for the dictionary generation. So we model the user's thinking process when they choose a password as a selection function. So a selection function only takes 2 parameters. One is a gesture type. There are only 3 types of gestures, like a tap, circle, line. And then is a point of interest attribute. That could be anything. Could be face, could be eye, could be a color like red, could be a circle. Then the selection function, when we apply the selection function to a picture, obviously it will generate many different gestures, right? And 3 gestures becomes a password. For example, let's say there is a selection function called the circle face, which means we're going to circle a face in the picture. If the picture has more than 1 face, then we circle all of them, right? There are multiple gestures. The line 2 noses, then we're going to line 2 noses together in a picture. So how do we automatically extract this kind of selection functions or these patterns from our training data set? So what we do is we compare the password with point of interest. So the point of interest is generated using computer vision tools. So let's say left-hand side, I have the password, 1 circle, a line, and a tab there. Then on the right-hand side, we use this one is an ideal case. We assume the computer vision tool is so accurate. It can identify 4 faces or the eyes and nose. Then we just compare the location of those gestures and the point of interest. Then we can say that, for example, the first one, we know this is a circle, and we know this location, this is a face. Then very naturally, we know the first gesture is circle or face. Then the second gesture, we know it's a line or nose, and the third one is table nose. Now, let's say we have those gestures. How do we really generate the password? What we do is we apply those selection functions back to the picture. Let's say the first function here is circle or face. Then we apply this function back to this picture. What we get is 4 gestures because there are 4 faces, right? Then the second function is line, 2 noses. Then we generate another 12 gestures. The third one is table nose. We generate another 4 gestures. So you can see that then by combining all those gestures together in those 3 steps, we are able to create a dictionary with 192 passwords. Okay. And the original password is in that dictionary. It's one of them. Okay. So it's not like we are going to crack the password in the very first try, but we know the password is in that dictionary. So that's our basic idea to extract and apply those selection functions, the patterns. So all those steps are automatic using computer vision tools. Then the next question is, we generate a lot of selection function here. Okay. Each selection function represents one way of choosing a gesture. And if we apply those functions to a picture, we get the password. But how do we rank those passwords? So ranking the password now becomes a problem of how do we rank those gestures. Then I designed 2 algorithms. One is called best cover. That one is basically a NP complete problem. We proved that in the paper. So the goal of that algorithm is to optimize the guessing order for password in the training data set. So if we apply that algorithm back to our training data set, it will generate the optimum guessing order, the least number of guessings to crack all the password in the training data set. But the problem with that approach is the training data set may be biased in the first place. Let's say our training data set only have 10 pictures, and 9 pictures of them are picture of people, and it's all clicked tap on eyes. Then tap on eye will be a very most used pattern there. However, if we apply this to a different picture which do not have eyes, or different data set where the pictures do not have many picture of people, then this pattern doesn't make sense there. That's why we have another algorithm. We call it unbiased algorithm, which is to reduce the POI distribution, a biased POI distribution in the training data set. And we evaluated both algorithms in both data sets, and some very interesting findings there. So this slide shows how many passwords we can crack using our approach. The green, this is using the best cover algorithm, and the green line is for dataset 1, the blue is for dataset 2. As you can see, in dataset 1, with 2 to the power of 18 or 19, so how big is that? It's maybe 500,000 guesses. So with 500,000 guesses, in dataset 1, we were able to crack almost half of the passwords. It's still a big number. 500,000 guesses is still a big number. But actually at here, at the index 0, I believe we cracked like hundreds of passwords. So some people choose very weak passwords that we can crack in even the first try or first 5 tries. For dataset 2, we can crack 25, a quarter of the password, also using 500,000 tries there. You can see, interesting part is dataset 1, they choose relatively weaker password. One of the reasons we believe is because dataset 1 was students. They are choosing password to just to access kind of like the course website. There is not really any sensitive information behind this authentication. They do not have their scores there. They only have those syllabus, lecture notes. So they have the tendency to choose weaker password so they can log in the system faster. But dataset 2, it's more like a role play. We ask them, imagine this is a password system for your BOA account, and then they choose stronger password. We also analyzed the passwords for individual pictures. For example, I will show you, there were several very simple pictures. In this picture, those are 2 pictures. The point of interest is the number of point of interest is very small. Just a airplane there. Besides that, nothing there. Then for this picture, even the first try, we cracked 13 passwords. 13 means there are 13 people. They are choosing almost the same password on the same picture, and our system were able to crack them in the first try. Because there are not so many point of interest there, you can say for this picture, our password guessing system only generate 600 passwords. And in that 6,000 passwords. And in those 6,000 passwords, we can crack like 14% of the user's passwords. We have almost 800 people. We can crack 18%, 40%. This one, our password system also only generate like 30,000 passwords, and we were able to crack 31% of all the passwords. Then a picture of people. We have several pictures, and you can see similar results. For those 2 pictures, similar results. We crack 29% of pictures in 500,000 guesses, which is obviously not as good as this one. This one is only 6,000 guesses. Here, because the picture is more complicated, there are more point of interest there. However, even the first guess, we were able to crack 9 passwords. So 9 people choose very weak passwords there. For complicated pictures like this, okay, this is just a bicycle, several different colors. There is a concrete wall behind that. Looks like there are a lot of point of interest, but nothing really stand out, right? If you think about how you are going to choose a password here, it's not as straightforward as something like this, right? So for this one, our system only cracked like 10% of passwords in 500,000 tries there, which is still good. Okay, so that's basically my picture password experience. So the takeaway here is as long as you allow users to choose passwords, they are going to choose some easy to remember but weak passwords, no matter it's text-based or picture-based. Any questions? So, good question. So, for text-based password, there are always some policy, right? You choose, you have to have some strange characters, and has to be 10 characters long, right? So what we do with this project is, our password guessing system can be easily reshaped. Here we call it attack, right? But we can also easily reshape it as a measurement. Strength picture password strength meter. For example, give me a password, then I use my system to check how many trials I need to break your password. Then use that trail as a metric whether this is secure or not, right? If I can crack your password in just 10 trials, then this is a very weak password. If I cannot crack this in 500,000 trials, I consider this is a very strong one, right? So the attack system basically is the same thing as the strength meter. So what we actually did is we got a patent for this for strength meter. We cannot patent the attack system, but we can patent the strength meter, but it's the same thing, yeah. It was back in 2012. The machine learning knowledge I have that time was only SVM. I was using SVM a lot, but it seems no one is using that anymore. Yeah. So definitely we can apply those new deep learning things for all kinds of problems like this. Yeah. Other questions? Okay, so Wednesday we will talk about those token-based. There will be more crypto stuff involved. Then Friday we talk about biometrics. I actually also work on biometrics, so I will use my own experience there, several papers to explain how it works. Okay, see you guys Wednesday.